Welcome back. We are doing thermodynamics homework solutions for Thermo 1. This is homework 6-2. Homework 6 is on semi-batch systems, also some other things like reactions and such. So, number 2 is straight from Koretsky's textbook, 5.38, just A, not B, just A. So, it says, consider filling a gas cylinder with ethane from a high-pressure supply line. Okay. Before filling is initially empty, so N1 equals 0. The valve is then open, exposing the tank to a 3 megapascal line. Okay, so P coming in is 3 megapascals. Okay. At 500 K. Okay. Until the pressure reaches 3 megapascals. So the final pressure in the tank is going to be 3 megapascals. Okay, basically, until it reaches mechanical equilibrium. Okay, the valve is then closed. Okay. The volume of the cylinder is 50 liters. Okay. Alright, for ethane, use the truncated variable equation to state in pressure. Okay. So it says that Z is equal to 1 plus B prime P. Okay. Okay. And it says B is constant. Okay. What is the temperature immediately after the valve is closed? Okay. Basically, what's T2? And, well, it doesn't say it, but, usually with the tank filling, it's rapid or it's adiabatic, so let's assume that. Otherwise, I don't think we can solve this. Okay. So we're going to assume that there is no exits, that it's adiabatic, there's no work, there's delta KE, delta PE are pretty much 0. There might be some other ones that I'm not thinking about. Well, we'll get there, right? It's not an ideal gas. And it doesn't say anything about heat capacity either, so because it gives us a real chemical. So we probably can't assume heat capacity is constant either. Okay. Let's see here. So, first we want to do our mole balance. Well, we draw a picture and we drew a boundary. Okay, so N dot I minus some exit N dot E equals dN dt control volume. Okay. So, this is 0. This becomes N dot I equals dN dt of control volume, which if I take out the time term, like this, it becomes dN, which is N2 minus N1, which is 0. So N2 is equal to minus N dot I delta T. Okay. All right. Simple enough. Okay, and then we go to our energy balance. So, summation of N dot I, HI plus 1/2 E squiggly squared I plus GZI minus exit N dot E, HE plus 1/2 E squiggly squared E plus GZE plus Q dot plus work dot equals D capital U, EK, EP, dt, CV. Okay. So, that goes to 0, 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 that goes to 0 because of the kinetic energy and potential energies. This whole thing goes to 0 because there's nothing coming out. This goes to 0 because there's no work, and this goes to 0 because it's adiabatic. So what I'm left with is N dot I, HI equals du dt of control volume. Okay, so we're pretty good up to that point. Now we need to simplify this. Now, the answer is very common for this problem, okay? But it's important to show your steps to show that, like, oh, well, instead of hand-waving how things happen, okay? So we have n dot I, okay, and if we get rid of the terms, we have n dot I delta t hi, and that equals d capital U, which is equal to n2 u2 minus n1 u1. Okay. Well, there is no initial moles. We've already established that. Okay, so I have n dot I delta t hi equals n2 u2. This is where people kind of get, oh, I don't know why there's a minus here. This is where people kind of get a little, they're just like, oh, well, they're, they kind of go from here to the final result. Well, you want to show this, and now I can see ni delta t equals n2, and so I can cancel those out and get hi equals u2. But it's important to have these kind of two steps to show that you know what happens to the mole aspect, and you don't just make it go away magically. Okay. So that's half the problem. Okay. Well, more like 3/4 of the problem. Okay. Hi equals u2. Now we just need to kind of get hi and u2 into a place where I can actually calculate it. Okay. And again, this is a departure function, so this is going to be a little goofy, but hey, that's okay. Alright, so let's erase some of this. I got my final result, so let's kind of erase everything except for my equation of state, and well, except for my equation of state and my assumptions. Alright, so I have hi equals u2. Okay, I'm going to rearrange this. Okay, so first of all, let's deal with z. Okay, so z equals this. Well, we need to get it in terms of stuff. Okay, well, if we cover that up, what do we have? That's right, we have p's. So we just need to get this in terms of like v equals. And this is p over rt plus b prime p. And so v equals rt over p plus b prime rt. Okay. All right, that's pretty simple. Okay, and again, b is known, it's a constant. And so, yeah. Okay. But I have this, so my departure function is going to be on a basis of p and t. So, I'm going to go from here to here, so to speak, but I'm going to go down to 0, come over here, and come up. And this is at 0. Okay. So, now because it's p's, okay, it is easier to deal with enthalpies than it is with energies. Okay. So let's rewrite this with respect to enthalpies. Okay. So we have hi minus u2 equals 0, which equals hi minus h2 minus p2v2 equals 0. Okay. Oh, sorry, plus. A minus a minus. Okay. And so, now, so if we rearrange it again, we have R2T, because it's an ideal gas. Oh wait, it's not an ideal gas. Yikes. So I have P2V2, okay? So I need to, now, I know my final pressure, I can get my final thing, RT over, so this, our P2V2 basically becomes P2V2 equals RT plus B prime RT2 times P2. Okay. All right, and that equals my delta H. So I have minus delta H departure of T2 P2. No. Well, let's write it this way. I kept my P2, so it becomes H2 minus HI. Okay. So I've got RT2 plus B prime RT2 P2 equals minus delta H departure function of TI PI minus or plus delta H of an ideal gas plus delta H departure of T2 P2. All right. And for my departure function, delta H departure function, well, that goes from an ideal gas to real for dH dP at constant T. dP, so this equals 0 to P, dH dP constant T minus dH dP constant T of an ideal gas, but this goes to 0 because it's an ideal gas. Well, enthalpy is only a function of temperature for an ideal gas. If it's kept constant, 0. Okay. dP, all right. And then, so our dH dP constant T is equal to S dt dP constant T. Oh wait, that's not right. TdS dP at constant T plus VdP dP at constant T, which is 1, and this is why it's simpler. Okay, and this equals minus T dV dt at constant P plus V. Okay, and so I'm going to take my derivative. Okay, I'll do that over here. So dV dt at constant P is equal to R over P plus B prime R. Okay. So plug it back into our we plug it back into our departure function. Okay, we're going to have, so delta H departure function is going to equal 0 to P of V, which is RT over P plus B prime RT, minus T times that guy, so minus RT over P minus B prime RT. What do you know? Everything cancels out. And we get 0. So, when we're all said and done, we have RT2 plus B prime RT2 P2 equals CP dt from Tn to T2. Okay. I can do the integral on that. I don't really want to do the integral on that, so we're going to assume it's constant for this one, but it's not. Okay. And so this becomes Cp T2 minus Tn. Okay. Well, I know Tn, I know Cp, because I look it up. I know P2, I know R, I know B prime. I know everything I can solve for T2. Okay. So at this point, it's just algebra. Okay. And that's just the way that departure function works, so to speak. Okay. But in terms of, and again, in terms of tank filling problems, yeah, it's always going to be H equals U, so to speak. But it's important to show where that comes from, or at least where do the moles go to.